In section 3.5 here, we're going to talk about compound interest and continuous compounding. So our main goal is to apply the compound interest and continuing compounding formulas for given situations. So let's check it out. Congratulations, you inherited $20,000. I wish it was true. Your grandparents suggested that you invest half of it in a fund to start a retirement, and your grandfather claims that an investment of $10,000 can grow to over $500,000 by the time you retire. That would be nice. Let's see if that's true. Okay, so we're going to start off supposing that we're going to invest that $10,000 into an investment account at a 3.5% annual interest. I want to know, what is the interest that would be earned after 1 year? So we're going to take our $10,000 times 0.035 to figure out the amount of interest earned after 1 year. This is just simple interest right here. All right. And that gives us $350. So we would earn $350 after 1 year. Suppose I left the money in the account for 10 years. Can the total amount of interest on the investment be calculated by multiplying my answer from part A by 10? Well, I would say no to that, because usually if you have an investment that you don't touch, the money that you earn goes back into the account, and then you're going to earn interest on that interest for the next year. So I would say no, because you earn interest. Earn interest on previous interest. Okay, then the second half of this question, let me move decimals out of my way here. The second half of this question would be, what assumptions are you making if you said yes? So if we said yes, our assumption would mean that the interest earned went somewhere else, that it went into a different account, not the same account. Okay, if yes, then the interest is not deposited in the same account. I had an account like that once. It's a mutual fund or something like that, I believe. And the interest earned went into my checking account, not into the fund. And so you were not able to earn interest on your interest. A long time ago. I don't have that anymore, but it's possible that could happen. Okay. Recall that for simple interest, the interest earned during the first period does not earn interest for the life of the investment. So if we did our simple interest of 3.5%, and then we did it for 10 years, we would earn an interest of $3,500, but we would not earn any interest on the interest earned. And who wants to do that? If you're going to keep this money in the account for 10 years, you should earn interest on your interest. So we would like to have compound interest instead. So this case up here was simple interest, where you don't get to earn money on the money you've already earned. Compound interest lets us earn on what we've already earned. So if I'm going to work on compound interest, I would take my $350, I would add it back into the account, and then I would have $10,350. Then I would be earning that 0.35 on the $10,350, and I'd get another $362.25 this time to add into the $10,350. After 2 years, I'd have $10,712. So I've earned slightly more interest in the second year. I earned $350 in the first year. I earned a little bit more interest, just a little bit, because I got to earn interest on my interest. So my balance increases by a little bit more each year. Sounds good. I would like my account to do that. Okay, so in this system, the interest can be compounded one time per year, but banks don't always just compound one time per year. They can compound every year, or they can do it quarterly. A lot of times you'll hear about investments with a quarterly report, or they can compound monthly. Savings accounts usually will compound monthly, or they could compound daily. Sometimes stocks and stock markets, where things change very rapidly, will compound daily. So there's a lot of different ways that things can be compounded. So our compound interest formula is going to factor in n, where n is the number of times the interest is compounded, in addition to the usual parameters like p, which is the amount that you invest, the principal invested, r, which is the annual interest rate, and t, which is the time in years since the money has been invested. All right, there's an example we can look through, but I'm going to flip our page to number 2 and keep working on this $10,000 investment. All right, so first of all, we're going to suppose that we deposit our $10,000 into an account with a 3.5% annual interest rate. So our rate is 0.035. And annual interest rate is usually abbreviated APR for short. So they are giving us that tidbit as well. And the interest is going to be compounded annually. And so n is going to be 1 for this one. Okay, so we're going to put these variables into our function. So the total amount that we're going to earn is going to be our principal, which is $10,000, times 1 plus, if you refer back to the formula, p times 1 plus r over n to the nt. So p times 1 plus r, interest rate, 0.035, over n is the number of times compounded per year, it's 1, to the n, which is 1 again, times t. So as a function, this is going to be my a of t function. So I don't know t. I'm going to actually squeak in my function notation here. A of t equals. So instead of equation notation, now it's in function notation. Use the compound interest formula to determine your balance at the end of the first year. All right. So A of t equals 10,000 times 1 plus 0.035 divided by 1. That was supposed to be a plus. I hit the wrong key, or I didn't hit shift, I guess. To the 1t. So if I evaluate this at 1, a of 1 says that at the end of the first year, I have $10,350. That's exactly what happened over here, right? Because in this situation, we were compounding it just one time per year. At the end of the year, we had earned $350. So with a 1 in the end position, it's doing, sorry, my decimal is in the way. It's doing the same thing that we were doing over here. Okay. What was the amount of interest earned in the first year? Well, since I had started off with $10,000, if I subtract the $10,000 back off, I can see that yes, the amount of interest earned was $350, like we started off in the simple interest case. All right, so now we're going to use the same formula to complete the following. How much do I earn after 2 years and 3 years and 4 years? I'm going to make a table because I can. And we're going to have our 0, 1, 2, 3, 4. And let's go ahead and evaluate a of 1. Not a of 1, a of x1. Gotta type what I mean here. All right, so 10,000, 10,350, $10,712.25. That one we had also seen in the previous page. If you flip back, you'll notice that for the second year. Then we have $11,087.18, and last, $11,475.23. The compound interest formula is an exponential function. Identify its base. Okay, so the base of the exponential function is actually going to be all of this part of it. A is the coefficient. Anything that is being raised to the t, including this 1 in the power, is part of the base. But I can calculate the base by doing all of that part of it. So if I do 1 plus 0.035 over 1 to the 1, that'll show me the base of this exponential function. So let's go ahead and compute that. Actually, I'm just going to copy it, paste it. I got to put the power 1 back on when I paste because I didn't manage to copy all of that. And so the base is 1.035. Is the base a growth or decay factor? Explain. Well, it's a growth factor. And I know it's a growth factor because it's larger than 1. So when I explain, it's because 1.035 is larger than 1. Now, I'm not surprised that this is my base since my growth rate was 3.5%. And remember, if I convert that into a decimal and add 1, I get my growth factor. So the growth factor is 1.035. The growth rate associated with it was 3.5%. Okay. Now, we're going to change this and say that we grow quarterly instead of annually. So the only thing that's going to change right here is going to be n. It's going to be n equals 4 for quarterly, 4 times per year, instead of n equals 1. So we want a new function here. So a of t now is going to be 10,000 times 1 plus 0.035 over 4 to the 4 again times t. The n value shows up twice in the equation, so I have 4 in both of those positions. Now, what would the balance be after the first year? Okay, so I'm going to go back and change my equation. Let me expand that a little bit and get 2 4s here and here. Okay. So after the first year now, I can see in my table here that the balance would be from this new equation, $10,354.62. So I earned a little bit more money. So instead of, we move decimals out of the way, instead of the $10,350, I'm at $10,354.62. I earned $4.62 more because we compounded it 4 times that year. So I earned just a teeny tiny bit in the first quarter, a little bit more in the second quarter, a little bit more in the third quarter, and by the fourth quarter, it had added up to just $4 more over that year. Okay. All right. So enter the function to my calculator. Determine the balance every 5 years up to 40, and then record the values in the table on the next page. So I'm just going to do that when I get to the next page. So pause on that one. I'll do it over there. All right. Now, they want me to write this function in the form a equals b to the t. So I'm going to talk about this for a second. First of all, what is that? So if I notice in this function right here, this is all just a number. So 1 plus 0.035 divided by 4, that's all just a number. So if I copy and paste that, or just stick the 4 in the bottom here since I already have it written. Come on. That is actually where this number has come from. What they want me to do is take this function up here and write it in the form a times b to the t. And so to do that, I need all of this evaluated. So I need all of that evaluated to figure out what b is going to be. So I'm going to stick the 4 on that number on the 1.00875. So I'm just going to put my power here of 4 to write this function in that form. So the a value is still 10,000. The b value is 1.03546. And then it would be to the t. So we've done everything but the t. When we evaluated that, the t would have been next to that 4. So we have the 10,000. This is all just a number, 1.03546 to the t. I kept a bunch of places on that because I want to very clearly see that the base of this function when I compound it quarterly is not the same as the base of the function when I compound it annually. Had I rounded to 3 places, I might have said, hey, they're the same. They're not the same. And they shouldn't be because their outputs are not the same. So you're going to need to keep a few more places here if you want to write this in AB to the T form. What is the base of this exponential function? Well, like we said, the base is 1.03546. Okay. Now, deposit your $10,000 and compound it monthly. So we're going to do the same formula. Oh, and then daily. But what's changing here is n. Okay. So back over to Desmos. We'll get some fun with our table here. So in this function, what's happening here is that the n value is changing. First, I want it to be quarterly. Then I want it to be monthly. Then I want it to be daily. So I actually have something different I want to put for n. So I'm going to put n for n. And I'm going to make this a function that has 2 parameters, n comma t. So there's 2 things in this function that change. The years change, and we're going to make our table here. And we're going to go like they wanted us to do, 5, 10, up through 40. Expand this a little bit. All right. When I call this function now, I have to call it with 2 parameters. The first parameter I have is n, and n is the number of compoundings. So I want n equals 4 first. So I'm actually going to do a of 4, comma, x1. So initially, it was $10,000. If I go ahead and put 1 in here just for a second, you can see after 1 year, that's what we got for our quarterly. We had $10,354. So our function right now is working as expected. After 1 year, if we compound it quarterly, we had $10,354.62. I'm going to take that 1 back off because the table I need here doesn't need it. But just to make sure the function was working properly, I stuck it in there for a minute. Now I'm going to make other rows and call the function a again. But this time, I want n to be 12 for monthly, comma, the year values are still going to be found in our x1 list. So comma x1. And one more time, a of, we're going to do 365 for daily, comma, the year values, t's, are still found in our x1 column. Okay, so I thought it made a lot more sense just to write the 2 parameter function and fill in our chart this way. I'm going to write these down in my book. I'm going to pause because there's going to be a lot of writing. So you can see these values and you can compare after you've written them down to make sure that we have them all in there. So if you want to pause and do that, you can do that now. All right, so my table is complete. And in problem 4, it says that we calculated the balance, that was this thing up here, of the $10,000 deposit at the annual interest rate of 3.5% compounded at different intervals. Which account has the highest balance, and does this seem reasonable? Explain. So after 40 years here, the account that has the highest balance, after 40 years, we have $40,305, we have $40,469, and we have $40,549. So we have the most money in the account that compounds daily. Because you're earning interest on your interest more often. So you get to earn a little bit interest more frequently when you compound more often. So the daily account, which has an n value of 365, and this seems reasonable, yes, because it compounds interest. It earns interest on its interest most often. So even if it only earns a few cents a day extra, those cents add up to be over 40 years. It's still not a huge difference. It's just an additional 200 and so dollars, 200 and not quite $50 extra. So that begs the question of, if I can earn more interest by compounding more often, how can I get the best possible interest rate? How many times could I compound it? What if I went more than daily and said hourly? Let's compound it hourly, or maybe every minute. Where's the limit for the amount of money I'd be able to earn on this account? So that's where continuous compounding comes in. Continuous means like compounding all the time, not just every second, but like instantaneously compounding. I want all the interest I could possibly earn. So we got to figure out what this is going to mean. Okay, so we're going to get to that. The discussion on that really comes in the next couple pages. So, first of all, they're backing it up to talking about the growth factor when you have your compoundings. So, as we saw on the previous page, the base, everything but the variable, so the 1 point or the 1 plus 0.035 over 1 to the 1, or as we did for the n equals 4, the 1 plus 0.035 over 4 to the 4. All of this stuff was a number. So all of this stuff for any of these, whatever n happens to be, the 1 plus the rate divided by n to the n power is going to be the base of our exponential factor. That's going to be our growth factor when you have n compoundings per year. So let's take a look at how the growth factors relate into this so we can build up towards that idea of continual compounding. Now we're going to make a table where we're just looking at our growth factors. Okay, so let me bring my decimals over. I'm not going to get rid of that massive table I had earlier. I'm just going to go down to a new row. We're going to let b be a function of n, and it's going to be equal to 1 plus our rate, 0.035 over n to the n. And then I'm going to start a new table here with inputs of 1, 4, 12, and 365, and then we'll autofill b with x2 input values. Okay, so if, let me slide this to the side here, maybe down. If we're compounding just one time per year, our growth factor, since it was an original interest rate of 3.5% here, then it would be 1.035. So that's the one that we've kind of already discussed from the simple interest case. In simple interest case, your base and your growth rate pull together and they make the 1.035 for your growth factor. If it was, though, quarterly, I did this one as well, it would have been 1.03546. So it's slightly larger. If it would have been monthly, we haven't done this one yet, it would have been 1.03557. 1.03557. So just a teeny bit bigger, right? And then if we did it daily, 1.03562. I could just keep the 618. I don't need to round it to 62. I mean, that's what we see up there. I was just, this one was to 5 places. So I was going to do 5 places, but 6 is fine there as well. Okay. So this thing that we're calculating right here in the growth factor for these is called the effective yield. So the rate is no longer the only thing controlling the amount of interest, because the number of compoundings also controls the interest. So we need to look at the rate and the number of compoundings together to talk about the factor, and that's our effective yield. So our effective yield, it's called R sub E. The little e just stands for effective to differentiate R sub E from R, which is the annual growth rate. This was R. All of these had the same R, regular R. But R sub E, the effective yield, is computed with that B equals 1 plus R over N, R being the interest rate, over N, the number of compoundings, to the power of number of compoundings. If I want to compute the effective yield, I would just take these and turn them back into percentages. So subtract the 1, turn them back into percentages. Okay, So we'll do that down at the bottom. They want us to do that in number 7. So we'll talk some more about effective yield in number 7. Or yeah, 7B. All right. So first, 7A, if the interest is compounded hourly, then we need to figure out how many hours there are in a year. So there's 365 days times 24 hours. That would mean an end value of 8,760. So compute the growth factor B for hourly. Well, I already have this table going on here. So I can plug in the number of hours in a year, 8,760, and I can compute that the growth factor is 1.0356196. All right. And now we're going to do the growth factors. Effective yield from the growth factor. We're going to do the R sub E, the effective yield. Sorry, we have the growth factors already in our chart. So I'm going to add in another component here. We know that to compute the rates, whether it's a regular rate or an effective rate, we take our B and we subtract from 1, then we make it a percent. So I'm going to start with the B, which is the B of x2 that we have computed in the previous row. Those are all of our B's, right? And I'm going to subtract from 1. And then because I need to turn it into a percent, why don't I just stick the times 100 right here to convert it into a percentage? So it makes it easier for me to write down my effective yields. So the first one is 3.5%, as we knew. The second one is 3.546%. The next one is 3.557%. And the next one is 3.5618 or 3.562%. And we could do the next one for daily, just not in the chart. The chart doesn't have a space for that, but we can see it right here as well. The next one for daily is going to be 3.5619%. Okay, so technically I'm going to change this one back because it looks like this number here. It looks like this number is a little bit higher than this one, and it's not. This one really was, remember, 3.5618%. And so I do want to show that the more compoundings, the larger the number. So this was 1.8, this is 1.96, this one is bigger. So it's getting very, very small. So you need to hold a great number of decimal places to be able to see the difference and see the growth in these because they're not growing very rapidly. They're growing small, but we can also kind of see that they're converging towards something. And they're converging towards that continuous compounding. All right. So there's a discussion over here. I usually skip these discussions, but I want to talk about this one because it's kind of interesting. In this formula, we're trying to figure out what we're converging towards, and they want to rewrite this to take the rate and put it as part of the power so that I don't lose the rate on the inside, so that I can let my rate vary a little bit. So what they've done is they have rewritten this formula, the formula that we used before, the compound interest formula, and they've said that we are going to change the power on this to n over r times r, right? Because the r's would cancel and you would get nt. It's going to match up here. So they just added in this divided by r and times r factor. So they took our power n, they divided it by r, and they multiplied it by r. Okay. The reason that they did that is so they could substitute n over r just for a letter x. Okay. So because n over r is x, if you flip it, take the reciprocal, r over n is 1 over x. So r over n becomes 1 over x, right? R over n becomes 1 over x. And n over r becomes x. So that's where the 1 over x and the x come from. All right. So now what we're looking at is we want to look at just this inside piece That would have been the base. The 1 plus 1 over x to the x. We're changing the letters just to try to simplify it so we don't have two letters going on right here. So we're going to look at this function and see what's going on. Okay, I'm going to open up a new tab so I can still have this stuff, but I want to see something clean where the other stuff's not being graphed. So let's go ahead and I'm just going to call it f of x for right now, equals 1 plus 1 over x to the x. All right, so look at this, and in the table, why is there an error at 0? So I'll make myself a table, and we'll put in, say, 0, and then they want like up by hundredths in their table here. So let's do our f of x1 for this table. Why is there an error at 0? Okay, that's the first question. Well, when you put 0 in for the input, it's going to go into the denominator, and 1 divided by 0 is undefined. Okay, so there's a 0. There's an error at x equals 0 because you would have 1 plus 1 over 0 to the 0th power, and you can't divide by 0, so 1 over 0 is undefined. Okay, so can't put in 0. Then they want us to explore what happens for the very large inputs that we see here. Okay, so they want us to determine the output for 4,000. So I don't even need some of these smaller ones. Let me go ahead and take them back out. They want us to see, say, 4,000. They want us to see 5,000, and I don't know why they didn't go 10,000. For some reason, they picked 10,500. Don't know. So what happens to the output? Okay, so I'm gonna shrink this up a teeny bit so I can write on my book. So for 4,000, we see 2.71794. For 5,000, we see 2.71801. And for 10,500, we see 2.71815. So what happens as these get very large? So this output value, it starts at 2.70 at 100. And if I just do like one more, let's do like 1,000, say. If I do 1,000, it's 2.716, and it's 2.717. They're getting closer, 2.718, 2.718. So they're keeping more decimal places as we go down. It started off just 2.7 wasn't common. Then it was 2.71 that wasn't common. Now it's 2.718 that's in common. So they're converging on something. So they're getting closer and closer to something. Okay, so these are getting closer to something. 2.718 something. And they studied this a whole lot in 1707 to 1793 when Euler was alive. And they defined this to be Euler's number by E. And so E is an irrational number. If you type the letter E on decimals, it's going to tell you what it's equal to. So E is 2.7182846, etc. 71828182846, etc. So I only can see that many decimal places right now. If you searched online, you could probably find more places, but this is decimals is routing. They're not going to give me more places on this particular screen. So how does this compare to the result up here? We can see that, yeah, that's actually what we're approaching. Our 2.718 number is what we're approaching. So this whole number, it's like pi, it's not repeating, it's never ending, it's a very long number. So E is the whole thing, but that's the value that we're approaching. If we were able to compound this more and more and more and more times, then we would get to this. This is our perfect base of our exponential function. So we were wondering what the perfect base was going to be, and it's going to be this number E. All right, so let me get rid of, oops, this right here. So if you recall, we rewrote the function so it was not dependent on the interest rate. The interest rate is still in the power now, and we have that e in the base. So our continual compounding interest rate is going to be a times p times e to the RT, where p is the principal, r is the annual interest rate, t is the time, and e is that special number. It's approximately 2.71828 and so on. It's not, you don't need to type in that number, but it's a special reserve number. It's the perfect base for compounded continuously. Continuous compounding. Okay, so number 10, we're going to calculate the balance of our $10,000 investment if we compound continuously. So I'm going to take my function back over here, and I'm going to add in a new one. I'm not going to call it A just because I called this function A, and I can't have two functions named A, so I'm just going to call it B just because. But I'm going to do B of t equals, and I know that my function, I should write this down. I'm going to write it right above here. I'll write A of t in my book because that's the A stands for the amount. I'm just going to use B when I type into decimals because I've already used A. But our principal was $10,000 times E to the rate. The rate was 0.035 for 3.5%, and then times T, which is the number of years. That's the function I'm going to type in for my B of T function here. 10,000, I hit the letter E, and then to the 0.035 T. Okay, now they want me to calculate the 10-year annual, the investment after 10 years. So I'm going to do A of 10. I'm really going to type B of 10, because I just didn't want to get rid of my previous function. But it's the same function. I'm plugging 10 into it. And so I get $14,190.68. Right. Compare that over here. Get rid of decimals. After 10 years with 4 compounding, so it's 14,169, 12 compoundings, 14,183, 365 compoundings, $14,190.44 to $14,190.68. So it's very close. We only got 28 more cents by going to compounded continuously, but there's no number of compoundings that could have got us more amount for this one. So we were almost there with daily. If you had gone to hourly, we might have gotten like 10 more cents, but continuously, 28 more cents for that value right here. That's the most we could have ever achieved at that interest rate. Okay, the formula used for the preceding result was, oh yes, same thing I had to write up there. If I compare those two equations, it shows me that the base of the exponential function is everything under the exponent that's numeric. So they're saying that the base is the e to the 0.035 because that's everything with the t. Okay, so we want to figure out that value. All right, I'm going to do that down here. So if I do e to the 0.035, that gives us the growth factor, the base of 1.035. Can't stop there because that's the original base. 6197. Okay, so again, trying to compare this with our bases that we had over here. When n was 1, it was 1.035 stop. When n was 4, it was 1.03546. When n was 12, when n was 365, etc., it was 1.03562. Now it's 1.03519. Hold on, that looks a little smaller, so I got to compare up here. For 365, it wasn't exactly 6.2, remember it was 618, and so this one is 61897. So it is bigger if I make sure to keep enough places to be able to compare them. So if I compare 1.035618 or 1.035696 for hourly, I'm at 197 here. I'm just an itty bit bigger because I have the perfect continual base where it's not just every hour or every second, it's continuously all the time compounding and adding on to the interest. That's the perfect base. Now, this one has the interest rate factored into it because I've used the 0.035. And so this one would give me an effective yield, R sub E, of, take off the 1, move it 2 places, of 3.56197%. So even though the annual interest rate is still 3.5%, the effective yield is 3.56197%, slightly higher than 3.5%. Okay, that is, I believe, the end of that situation in the I get an investment situation. Okay. Now we're starting a new situation. Beginning in 2018, the Federal Reserve kept its lending rate low. This resulted in low interest rates on both deposits and loans. So in 2013, the interest rate paid in a premium savings account was 0.85%. Determine the interest rate created by a 10% deposit after 1 year if the monthly was 8.5% compounded quarterly. Okay, so I'm going to come back to that just a second. I forgot before I clear my Desmos graph what I wanted to do. I thought it was going to ask me about this, and I'm going to do it before we get into that new situation. I'm going to add my B of T column over here and put the X1s into it. So we already did the comparison for 10 years, how this one came out just a teeny bit higher. Just wanted to show again for the 40 years, we're not much higher, but yes, we're higher. And all of these are getting bigger and bigger and bigger until they reach that perfect continuous compounding. So I can compare if I add another table in here for this one. Wanted to share that before I got rid of this graph. I'm going to go into my new graph here and talk about the new situation. All right. So first of all, it says what I should do is determine the interest created by a $10,000 deposit after 1 year if the money was deposited at 0.85% compounded quarterly. So they're giving me the principal, they're giving me the amount of time, they're giving me the interest rate, and they're giving me the number of compoundings, N. So the amount is going to be 10,000 times 1 plus R. This needs to be converted into a decimal, so we're going to move the decimal place 2 spaces, so 0.0085 divided by N, which is 4 for quarterly, to the power 4, again for quarterly, times 1 for 1 year. This is not a function because I don't have any variables in this situation. This is just a number. I need to simplify this number to figure out the amount that I have in the account. So I can type it in as 10,000 times 1 plus 0.0085 over 4 to the power 4, I can't put the times up here. Notice if I put times, it like pops it down, but I could do a parentheses instead of the time symbol. So I'll do that, 4 times 1. All right. So this gives me, let's see, $10,085.27. That does not actually answer the question. Since the question wanted me to determine the interest, I would have to subtract off the $10,000. But luckily I can subtract out 10,000 in my head right here, and it's just the $85.27 in interest. Because if you subtract out the $10,000, the 10,000 part goes away, and you instead of 10,085, you just have 85.27. So this is the final amount in the account. How much interest? $85.27 in interest. Okay. Now, determine the value if we have the same amount of money deposited for 5 years and we're going to compound it monthly. Okay. So our A is going to equal $10,000 for our principal again, times 1 plus the interest rate, still 0.0085. We're compounding monthly now, so the number of compoundings is 12. And then to the 12 times 5, because we're going to compound for 5 years. Again, that's not a function, it's just a number. I can take the base of this and just change a couple pieces. I'm going to change the number of compoundings from 4 to 12. I'm going to change that up here as well as 12, and we're going to change the number of years to 5. Everything else remained the same. This time it doesn't ask me to determine the amount of interest, it actually asks me to determine the value. So I'm not going to have to subtract off the 10,000. So the value of this account would be $10,434.00. Okay. C, determine the value in the account deposited after 10 years the money was deposited at the same interest rate, but this time compounded continuously. So this time I need to start anew because I'm going to be using a different equation. If I'm going to compound continuously, it's going to have the 10,000. I should write it down first. It's going to have the 10,000 times e to the r, which is 0.0085 again. And then times t, again, this time it's going to be 10 years. So we're going to put 10 in this case. And we're going to determine the value in the account. So we'll have our 0.0085 up there times 10. And after 10 years, there is $10,887.17. Moving that over. Part T asks us, do we believe that keeping interest rate low encourages savings? Each of these is very different because they have a different quarterly, a different compounding rate, and a different number of years of savings. So after 1 year, I only saved $85 in the account. After 5 years, with even more compounding, I saved $400, but that's 5 years and $400. That's not much. 10 years, $800. So the answer is no. Low interest rate don't encourage savings because you're not really earning very much. 10 years, I only got $800 out of my savings. I mean, it's $800 I wouldn't have had, but that's still $800 you could have been, you could $10,000 you weren't able to spend that entire time. If I had $10,000 I couldn't spend it at all, I only earned 800. So low interest rates don't encourage savings. You don't earn very much if the interest rate is low. What low interest rate they do is they encourage borrowing. So if we flipped this and thought about it as a loan instead of an account, hey, I only have to pay $800 after 10 years. I get to borrow $10,000 for 10 years. I only owe 800. Cool. So they encourage borrowing when the interest rates are low. They don't encourage savings. Okay. So back over to the last question, number 12 here. Historically, investments in the stock market have yielded an average rate of 11.7% per year. So we're investing a lot of $10,000 here. We're going to invest $10,000 again in an account with an 11% annual interest rate that compounds continuously. Use this formula to determine the balance after 10 years. Okay, so first of all, my account is going to be, I'm going to write the function a of t, and then we'll stick in the 35 because I'm going to want to use that same account in a moment for 40 years. So the principal is 10,000 again. It's compounded continuously, so that's times e to the 11.7 converted into a decimal is 0.117. And then t, that will be our formula for this account compounded continuously. And then we're going to be able to evaluate this at 35. And then down here, we'll be able to evaluate the same formula here at 40. So let's put it in as an equation. All right, so there's my formula, and we want to evaluate A of 35. So after 35 years, a $10,000 investment would have grown to, whoa, $60,393.39. And after 40 years, it would have grown to $1,077,700.73. So, my grandfather claimed that $10,000 could grow to more than $500,000 by the time you retire. So, depending on how old you were when you got the investment, if you still had about 40 years to work, then is your grandfather correct? If you stuck it in the stock market and you had a rate of about 11%, then that was possible, right? So you'd say yes, even if you considered a little bit of ups and downs in the stock market. If you can reach $1 million after 40 years, then you should be able to get $500,000, even if there's some ups and downs. Yep. So you should be able to um, at least $500,000. Okay. Now, again, this is best case scenario because it's compounded continuously. And the stock market does not compound continuously. It perhaps compounds daily. However, if best case scenario is $1 million, then, worst case scenario, we should be able to get half of that is what we're trying to say with our predictions. So, yeah, $500,000 does sound reasonable based off of this interest rate. I have to check more recent statistics to see if that's still the average yield. If this was just the average yield in 2020, it's the pre-pandemic average yield. I'm not entirely sure what the most recent information tells us. All right, so note the important formulas for this section. We have our compound interest, where the finite number of compoundings, n. We have our compound continuous, where we have a continuous number of compoundings defined by the e. And then we can talk about, this is just talking about if you increase the number of periods, then this formula is approximated by this formula. They merge together if you talk about compounding over and over and over.